Okay, last class I explained about the shear stress distribution in a beam. So we have derived that shear stress expression, that is Q is equal to uh, F into AY bar divided by B into I. So that is the expression. See, this is the expression. Q is the shear stress, F is the shear force at that section, B is the width of the section, I is the moment of inertia about the neutral axis, A is the area above that width which we are going to consider in the cross section. Y bar is the distance of the centroid of that area A from the neutral axis. So this is what we have seen. And for rectangular section, we have proved that maximum shear stress occurs at the neutral axis and it is equal to 1.5 times the average shear stress. And the variation of shear stress with respect to distance from neutral axis, that is y, is parabolic. So it contains y square term. That is why it is parabolic like this. It is zero at the extreme fibers. So shear stress is always zero at the extreme fiber because there is no area above this and there is no area below this. So A into Y bar term will become 0. So therefore the shear stress at the extreme fiber is 0, which is opposite to that of bending stress. Bending stress is maximum at the extreme fiber. Bending stress is 0 at the neutral axis, whereas here shear stress is 0 at the extreme fiber. And shear stress is maximum at neutral axis in the case of rectangular section. It is equal to 1.5 times the average shear stress that we have proved. Then circular section, I have asked you to look into that. Using the transformation, trigonometric transformation has been derived. In the case of circular section, maximum shear stress will be 1.33 times the average shear stress. See, that is 4 by 3. 4 by 3 the average shear stress. Once again, it occurs at the neutral axis level and the shear stress is 0 at the farthest fibers and parabolic variation as usual. And in the case of triangular section, we have shown that the shear stress distribution will be like this. Once again, it is 0 at the farthest fiber. Maximum occurs at what distance? Maximum will be occurring at a distance of see here h by 2. That is at half the depth. Maximum shear stress will occur, that we have proved, which is equal to 1.5 times the average shear stress. And at the neutral axis level, this is the neutral axis. So in this case, at neutral axis level, it is not maximum. Half the depth it is maximum. Whereas in the other two cases, in circular and rectangular, you have seen that shear stress is maximum at the neutral axis level. In this case, at the neutral axis level, it is 4 by 3 times the average shear stress. Average shear stress is F divided by this area of the section. That is the average shear stress or mean shear stress. So that means bending stress and shear stress both they will vary across the depth of the section when a beam is subjected to external load. Now today we will see some problems on T section and I section because they are also important. Maybe symmetrical or unsymmetrical. In T section we have two types, symmetrical and unsymmetrical. Whereas in I section it is only unsymmetrical because in I section you have symmetrical and unsymmetrical. In T section it is always unsymmetrical because it is not at all symmetry about one of the axes. So how the shear stress distribution will be there in such cases that we will see, and how we can plot the shear stress diagram in the case of T section and I section, that we will discuss now. Bending stress diagram is always straight line, whereas shear stress diagram is parabola. Now this is the problem. This is the I section with the geometrical details. This is top flange, this is bottom flange. You can see in this problem that this is 180. Please make that correction. This is symmetrical. They have given symmetrical I section. So if you plot the centroid, centroid will be exactly at the geometrical center of this I section here, and neutral axis passes through that centroid, and naturally maximum shear stress occurs at the neutral axis. That means if it is symmetrical, naturally neutral axis coincides with the centroidal axis, and maximum shear stress occurs at that level. Now we have to find these values. Some values are given here. I had to find the shear stress here at the top of the web and at the bottom of the web, and we have to plot the shear stress diagram. Now let us see how we can do it. formula remains same. So he has given that this section is subjected to a shear force of 100 kilonewton. So F value is 100 kilonewton. So the formula is Q is equal to F into AY bar divided by B into I. So that means I we have to find out first. Moment of inertia of this I section about the neutral axis. So in this case, since it is symmetrical, neutral axis lies here. So we have to find the value of I, moment of inertia of this I section about this neutral axis. So how to find that? So for that we have using once again the parallaxis theorem. So on that day I had explained the parallaxis theorem. So that you have to apply here. For I section and T section, you have to use parallaxis theorem. Now here this I section contains three rectangular parts. So your moment of inertia of this I section will be equal to moment of inertia of this rectangle plus this rectangle plus this rectangle about the neutral axis. Okay. Now we know that the centroid exactly lies at 200 millimeter from the bottom because total depth is 400 mm. So this will be 200 mm. Centroid of this I section will be exactly here at 200 mm. Now let us apply the parallaxis theorem for this top rectangle. So according to parallaxis theorem, so moment of inertia about this INA will be equal to moment of inertia about this centroidal axis, which is BDQ by 12 of this rectangle, plus the area of that rectangle into distance between the centroid of that rectangle and the neutral axis. Okay, that is a square of that. So we have given that. So INA is equal to IG plus A into YC square. So where YC is the distance between the centroid of this rectangle, top rectangle, that is top flange, and the neutral axis. So all those you will be knowing. So BD cube by 12 for this rectangle will be B is 180, D is 10, thickness is 10, depth is 10. So 180 into 10 cube divided by 12. See here, this is the term. 180 into 10 cube divided by 12 plus area of that rectangle 180 into 10 into distance between the centroid of this rectangle and neutral axis of this I section. That is, distance will be now, total distance is 200. From 200 you have to deduct 5 mm because centroid will be here. So 200 minus 5 square of that. So that is the first term plus for the second rectangle BD cube by 12 will be B is 10, D is 400 minus 20, that is 380. So it becomes 10 into 380 cube by 12. So it should be cube here. Please make that correction. Mistakes are there. So 10 into 380 cube divided by 12 plus, that is BD cube by 12 for this web portion, plus area is 10 into 380 into distance between the neutral axis and the centroid of this web, which is nothing but 0 because centroid of this web coincides with the centroid of this I section or the neutral axis. Therefore, 200 minus 200, that it becomes 0. So you can write it as 0. That is the moment of inertia of this portion plus the moment of inertia of this bottom rectangle will be similar to top rectangle. This is 180. Please make that correction. So BD cube by 12, 180 into 10 cube divided by 12 plus area 180 into 10 into distance between neutral axis and the CG of this will be once again 200 minus 5 here. So that is 200 minus 5 square. So if you add all these three, you are going to get the moment of inertia of this I section about the neutral axis. So this is the value. I is this. I means INA about the neutral axis. So this is the answer you are going to get after simplification. Okay. So it is expressed in terms of millimeter power 4. The unit of moment of inertia is millimeter power 4. Now let us find out the shear stress at different points. We know that the shear stress at the top fiber and the bottom fiber will be 0. See here, this is 0, this is 0. Now next, you move further. So let us move from the top. Now I want the shear force where the breadth changes. So here, the breadth changes here. See here, at this point, that means you can say that at the bottom of the top flange. Bottom of the top flange means this one. So if you take the flange portion, what will be the B value? Only B value will change. I value won't change, F value won't change. So A into Y bar will change and B will change. F and I remain same. F is 100 kilonewton here. So 100 kilonewton means 100 into 10 power 3 Newton. Then I value we have found out. 16 point something already we got 182.64 into 10 power 6 millimeter per 4. That is the I value. So in this formula, F divided by Bi into Ay bar, F is constant, I is constant. Okay, B A Y bar will change. Let us see how it changes. Now I am at this level. So this point is called as bottom of top flange. All of you observe here, very important. So here, when you take the flange portion, what is the width of the flange portion? So total actually 180 is the width at the top portion, but at the bottom it will be 180 minus 10. So this 10 we have to deduct. Web width we have to deduct. That becomes, it becomes 180 minus 10 means it is 170. So when you are finding the shear stress here at the bottom of the top flange, we have to take B is equal to 170. It is not 180. Please make a note of that. So in that formula, so F will be 100 into 10 cube divided by I will be this value, B will be 170. Please note that the shear stress at the bottom of top flange, this is the wording you have to use. Shear stress at the bottom of top flange, B, it is not 180. And what is this A into Y bar? That is very important. So A into Y bar is whatever area is there above this that is your A value, and Y bar is the distance of the CG of that area. CG of that area will be here. CG of the area will be here, and the distance of the CG of the area from this neutral axis will be 200 minus 5. That is 195. So that is your Y bar value. Please note that A is the area above this layer, that is bottom of top flange, which is 180 into 10 into Y bar is the distance of the CG of that area from the neutral axis, which is 200 minus 5, 195. So if you substitute that here, see here what you are going to get. So 100 into 10 cube is F value divided by 182.64 into 10 power 6 is the I value, and here it should be 170. It should be 170. Okay, please note that this B value should be 170. So it is not 180. You have to take it as 170. Please check that. So this should be 170 into I into area is, as I told, 180 into 10 into distance of CG is 195 from the neutral axis. So this is the value of shear stress at the bottom of top flange. At the bottom of top flange, which you are going to get it as 1.068. So if you simplify this, you will get 1.068 Newton per mm square. It will be Newton per millimeter square. This is one value. Now what happens? Very important. Observe here. Here what happens? There are two widths here. Suppose if you consider flange portion, width is 170. But if you consider web portion, width is 10 mm. See here. Now that means you have two values of shear stress here. You have two values of shear stress here. One value for B is equal to 10, another value for B is equal to 170. So that value is called as shear stress at the top of flange, web, at the top of web. You can call it as shear stress at top of web. See here. So that is the next shear stress in the web, but the junction with flange. Okay, like that also we can write, or you can write just shear stress at the top of web. So at the top of web, only difference here is your B value will be 10. Width of web we have to take. There you have to take width of flange. So here please note that this is it is not 180, it is 170. So I think 1 second. 120 only has taken. Okay. So that means you have to take 180 only. So 180 only we have to take, not 170. It is correct. Whatever he has done is correct. So please note that here. So here whatever 180 is taken is correct. So at the bottom of the flange, you have to take 180. At the top of the web, we have to take 10. Okay, please note. Yeah? Top of the web it is 10 because we have to take web width. When you are considering flange portion, you have to take the flange width. So here it is 180, there it is 10. That's all the difference. Remaining things are same because area above that will be same. Distance of centroid also will be same. Only difference is in B. So we are having two values of shear stress at this junction. So wherever junction is there between flange and web, you will be having two values of shear stress. So the first value is this 1.068. That is for flange. Second value is 19.217. It reduces because your B value increases. B value reduces, your shear stress value increases because B is in the denominator. So these are the two values. So 1.068 is the shear stress by taking B is equal to 180. 19.217 is the shear stress by taking B is equal to 10. This is web width, this is flange width. Please make a note of that. Now, you have to calculate the maximum shear stress also. We know that maximum shear stress occurs at the neutral axis level. So we know that the neutral axis in this problem coincides with the centroidal axis. So neutral axis means here. So for that, we have to compute the value of shear stress. So we have to calculate the value of the shear stress there. So once again here, since the neutral axis, what happens here, since this here you have the width B. At the neutral axis, the width is B. B is 10 here. Because it lies in the web portion, B we have to take 10. See here, if you want to calculate the shear stress here, maximum shear stress, which occurs at the neutral axis, we have to take like this. See here. So shear stress at neutral axis, F is 100 into 10 cube Newton divided by B is 10 because the width at that neutral axis level is 10 mm. Into I value, once again it is same, 182.6 into 10 power 6. So 10 power 6 is missing here. Lot of mistakes. Into 10 power 6 is missing here. Please make a note of that. Into A into Y bar. So this is important. Now A into Y bar, how to calculate? So what you have to do is, we have to take the portion above the neutral axis or below the neutral axis. So this is the neutral axis level. I have to take either above or below this neutral axis. I have to compute the A into Y bar for that area. So this is the area. This is the total. This area becomes a T section now. See here. Whatever area is there above the neutral axis, it is like a T section. Now what we have to do? So if you want the neutral axis, at the neutral axis, if you want the shear stress value, we have to take this for A into Y. In that A into Y bar, A is nothing but this entire area. Above the neutral axis, whatever area is there, that is A. Into Y bar is the distance of the corresponding centroids. Now, what you can do is here is very simple. So, if to find A into Y bar above the neutral axis, it consists of two parts. Two rectangles are there. One rectangle is web, another rectangle this flange. So, what is the area of this rectangle? Web rectangle, it is 10 into 190, I think. So, because, yeah, 200 minus 10. Is it not? So this depth will be only for the web. From here to here it is 190. So 10 into 190 is the area into Y bar. Y bar is the distance of CG of this web from the neutral axis, which is 190 divided by 2. Half of 190. Okay, that is 95. So please note that A into Y bar for this web portion above the neutral axis is A is 10 into 190. Into Y bar is 190 divided by 2, that is 95. That is for this web portion. Then for this flange portion, we have to add both plus. So for the flange portion, area is 180 into 10. 180 into 10 is the area. Y bar is distance of CG of this, okay? CG of this from neutral axis, which is how much? 200 minus 5, that is 195. So that is what we have to write here. See here, A into Y bar for this will be 180 into 10 into 195. This is for the flange portion plus 10 into 200 minus 10 is 190 into 190 by 2, that is 95. So this is for the web portion. This is what I told. So this is A into Y bar. So what we have done is, A into y bar we have written for flange and web separately and we have added. This is how we have to do. So area of the flange into distance of CG of flange from the neutral axis plus area of web above the neutral axis into distance of CG of web above the neutral axis from the neutral axis. Okay, that is the thing. So if you simplify this, you will get this much. This is the maximum value of shear stress which occurs at the neutral axis. Now, if you plot the values, how to plot the shear stress distribution? We know that at the extreme fiber it is 0. Then comes the bottom of top flange which is 1.6068. Then it comes to web portion, that is top of web which is 19.217. So at this level you have two values of shear stress. Then maximum will be at the neutral axis 29.1, and then since it is symmetric, the same thing will come here also. Okay, same values. So this value is 1.068, this value is 19.217, and this is 0. So this is because I section is symmetric, shear stress distribution also will be symmetric. So we need to calculate three values here. Shear stress at the bottom of top flange, shear stress at the top of web. There you will be having only the value of B different. For bottom of top flange, B is 180. For top of web, B is 10. Then you have here at the neutral axis, it is maximum. So we have to find the area above the neutral axis, and that should be corresponding area should be multiplied by the respective distance of centroid from the neutral axis. That is A into y bar for this web and A into y bar for this flange. So we have to add them. So then simplify that, you are going to get the shear stress, maximum shear stress at the neutral axis. So this is what is the problem. Next is this T section. So in the T section, it is similar to I section. Let us see how it can be done. In this case also, you can observe here the shear stress distribution will be like this. At the top fiber and bottom fiber, it will be 0, 0, 0 here. And here once again, you have the bottom flange, bottom of top flange and web portion. You will be having two values of shear stress. One by taking B is equal to 120, another by taking B is equal to 12. So here web thickness is 12, flange thickness is also 12, and flange width is 120, web depth will be 120 minus 12. Okay, it becomes 108. So these are the dimensions. So centroid will not be exactly at the center because it is not a symmetric section. T section is symmetric about only vertical axis, that is y axis. It is not symmetric about the horizontal axis. Therefore, we have to locate the centroid first. Then we have to calculate I. So in this case, because of unsymmetrical condition, T section is unsymmetrical. So we have to calculate the distance of centroid first. So y bar. So y bar distance or yt you can take. Let y bar be the distance of centroid of the section from its top fiber. So from the top fiber he has calculated. So from the top fiber we have to calculate the distance of the center. Either you can calculate from top fiber or bottom fiber, whichever is convenient for you. Let us see, in this case he has taken from the top fiber, which is nothing but yt. So y bar is nothing but yt here. Moment of area about the top fiber divided by the total area. That means when you are measuring the distance from the top fiber. So if you calculate the y bar distance, so there are two areas, like two rectangles are there here. There are two rectangles, one flange and one web. Rectangle area is 120 into 12. See here, 120 into 12, and its CG will be at a distance of 6 mm from the top fiber. So into 6. So this is your see here. This is the moment of this is the area. 120 into 12 is the area of this flange. Into distance of CG of the flange from the top fiber is 12 divided by 2, which is 6. Plus, then you take this web portion. What is the depth of this web? Depth of the web is 120 minus 12. That is what he has written. 108 into 12 is the thickness. So that is the area into distance of CG of this web from the top fiber, which is nothing but this 12 plus half the distance of 108. Please note that. That means 120 divided by minus 12 divided by 2. So 12 plus that. So this is the distance of this web from the top fiber. So this is this is A of the flange multiplied by distance of CG from the top fiber plus area of the web into distance of CG of the web from the top fiber divided by total area. So total area is area of this flange plus area of this web. So if you do that, you will get 34.40 mm. That is the distance of CG from the top fiber of this I section. So this is your CG of the T section, and neutral axis passes through this. This is the neutral axis. So this distance, please note that it is not written here. You can make a note. So this distance is 34.42, and what will be this distance? That will be 120 minus 34.42. So that from the neutral axis to the bottom fiber, it will be 120 minus 34.42. So first we have located the centroid. In the last problem, location of centroid was not required because it was symmetric. Exact center of the section will be the centroid and the neutral axis, whereas here T section is symmetric about only vertical axis. It is not symmetric about horizontal axis. Therefore, you have to locate the centroid of the T section to locate the neutral axis, and then we have to proceed. Next, I need the value of I value, moment of inertia about the centroid or neutral axis. It will be, once again, you have to apply parallaxis theorem. Now, be careful here. Now, this is the neutral axis. About this neutral axis, I want the moment of inertia. So, formula is BD cube by 12 for these two rectangles plus area of that rectangle multiplied by distance of CG of that rectangle from the neutral axis. Now, let us see here. This is the top flange. Now, let us calculate the moment of inertia of this top flange about the neutral axis, which is BD cube by 12, 120 into 12 cube divided by 12. Okay, 120 into 12 cube divided by 12 plus area is 120 into 12 into distance of CG of the top flange from the neutral axis will be. So this is 34.42. Just now we have found out that 34.42 minus 6. Okay, because CG is here. So 34.42 minus 6 square of that. So that's what is the I value of the top flange or the flange. Only one flange is there here. See here, BD cube by 12 plus 120 into 12 into 34.42 minus 6 whole square. This is for the flange portion. Now for the web portion, once again BD cube by 12 for the web portion. B is here 12, width is 12, depth is 108, 120 minus 12. Okay, so 120 minus 12 whole cube plus area is once again 12 into 108 into distance of the CG of this web from the neutral axis. Okay, so this is the centroid of the entire T section, but this for this web centroid will be somewhere here. What is the distance from the neutral axis? So centroid of the web will be, see here, web depth is, total depth is 108. Half of that we have to take. So 108 half means it is 54. So 54 mm, 54 mm from the bottom. So from the bottom or from this edge. Okay. So if you calculate the distance of this neutral axis from the centroid, so you will be getting how much? So this is 34.42. This we have got how much? 120 minus 34.42. So this distance. So from that you have to deduct this 54. So you are going to get the distance between those two and take the square of that. Take the square of that. So everything has been done here. You can see here. If you simplify that, you are going to get the moment of inertia of that I section about the neutral axis. Now, once you locate the centroid, once you get the moment of inertia value, then you can plot the shear stress distribution. So we know that shear stresses are zero at extreme fibers. Now we will calculate the shear stress at the bottom of the flange. At the bottom of the flange, only one flange is there here. You need not call it as top flange and bottom flange. You have to tell that in I section, not in T section. So here I want now. Here we know that it is zero. Shear stress is zero. Here, so there are two values of shear stress. That's what. Just like I section. So for one value of shear stress, we have to take B is equal to 120. For the another value of shear stress, we have to take B is equal to 12. That's all. That's all the difference. So now the formula is F divided by B into I into A into Y bar. So shear stress formula is this one. Shear stress formula, same, of course, same formula we are using here. So F here is 25 kilonewton. He has given. So F 25 into 10 power 3 Newton, converted kilonewton to Newton, divided by, first we will take B as 120, and we have got the value of I as this much, that we substitute into A into Y bar. See here, A into Y bar. What is that A into Y bar? So A into Y bar is, A is this 120 into this whatever 120 is there. So that 120 multiplied by 12. So area of this flange above this bottom of flange, whatever area is there, that we have to take in the formula. Small a represents this area, 120 into 12 into y bar means distance of the centroid of that area from the neutral axis. So it will be 34.42 minus 6. Please note that 34.42 minus 6. That is y bar. That's what is written here. See here. Y bar is 34.42 minus 6. Now you substitute in that formula. So Q at the bottom of the flange will be F divided by B into I into A into Y bar. Okay, this is what. So area is 120 into 12. Now coming to the other one, just by putting B is equal to 12 in the same thing, instead of 120, if you put 12, you are going to get in the web portion, because in the web, width of web we have to take, B will be 12. So for flange it is 120, for web it is 12. So if you put 12 there, naturally you will be getting 10 times more. It is 2.9, it is 29. So that means you are getting the shear stress two values at this junction. First we have to take flange width, then we have to take web width. Remaining things are same. Only B value will change when you are calculating shear stress at the junction of flange and web. So you are having two values, 2.9 and 29. Next, you have to join by a straight line, horizontal line, that's all. Then you have the maximum shear stress at the neutral axis. So we have located the neutral axis point, 34.42 from the top, or it is 120 minus 34.42. It comes out to be 85 something, 85.6 I think. You will get 85.6. 85.58, okay, 85.58 you may get. So that is the distance from the bottom fiber. Now let us see how to calculate the stress at neutral axis, shear stress at neutral axis. For this we can consider AY bar term above the section or below the section. It is convenient to consider the term below this level, because when you take below the level, it is very easy to write down the expression for A into Y bar. See, when you want at the neutral axis level, when you want the shear stress, either you can take above the neutral axis, whatever area is there, and we have tried that A into Y bar for that. Otherwise, you can take below that. So here, if you take above that, you will be getting two rectangles. Two areas we have to take, two values of Y bar we have to take. Otherwise, if you take below the neutral axis, you have only one rectangle. So only one area and one Y bar value. So that is why we are taking below the neutral axis. So F value is same, 25 into 10 power 3, divided by B also is 12 mm. At the neutral axis level, B value is 12, into I value remains same, so whatever you have got, into A into Y bar. So what is that A into Y bar? If you consider below this, whatever area is there below this neutral axis, what is that area? So this length will be 120 minus 34.42 into 12. So that is the area. Into Y bar is the distance of CG of this area from the neutral axis, which is half of that. That is half of that 120 minus 34.42. So that has been done here. See here. So he has written here, area is 12 into 120 minus 34.2, that is 85.58. If you multiply that, you will get this much. This is the area in millimeter square. And distance of its centroid from the neutral axis, naturally half of that. Okay. So put B is equal to 12 mm. This is what I told. So F is 25 into 10 cube divided by B is 12. I is the same value into area of that rectangle below the neutral axis. Web portion rectangle is this much into distance of centroid of that area below the neutral axis. From the neutral axis is 42.79. If you simplify this, you are getting 31.17 Newton per mm square. That is the maximum value of shear stress at the neutral axis. So if you plot that 31.77, you will be getting like this. 31.17, you will be getting like this. Now if you join this, so from here to here, it is a smooth curve. Then from here to here, straight line. Then smooth curve. That is a parabola. So this is a parabola. This is a parabola, and this is a parabola. Only here we have the horizontal portion. So in the case of I section, you have two junctions of flange and web. In the case of T section, you have only one junction of flange and web. There you have two values of shear stress. So this is about T section. Now one more problem, which is also important, I will explain. Unsymmetrical I section. So there also you will be getting the shear stress distribution. So here he has given the shear force value at this section as 60 kilonewton. So F value is 60 kilonewton or 60 into 10 power 3 Newton. Draw the shear stress variation diagram across the depth. Here the thing is, since it is an unsymmetrical section, you will not be having same values here, above the neutral axis and below the neutral axis, just similar to your first problem. So in this case, first we have to find out this centroid as usual, because centroid will not be exactly at the center. Your top flange and bottom flange, they are of different dimensions. The top flange is 100 by 20, bottom flange is 150 by 20, and wedge is 20 by 180. Okay, that is the dimension. So calculate the centroid. Locate the centroid of this I section. Once again, as usual, with respect to top fiber, it has been located. Y bar is calculated with respect to top fiber. There are three rectangles here. So first rectangle area 100 into 20 into distance of centroid of that from the top fiber will be 10. So 100 into 20 into 10. Okay, this is first part. For the web portion, area is 20 into 160, 20 into 160 into distance of CG from the top fiber of this web will be 20 plus half of 160. 20 plus half of 160. See, this is what. Okay. Next, we have for the bottom rectangle, area is 150 by 20 into distance from the top fiber to the centroid of this bottom rectangle will be 20 plus 160 plus 10. This is 10. Half of this. Here it will be there. Okay. That is 190. So this is the numerator divided by the total area. 100 into 20 plus 20 into 160 plus 150 into 20. So if you do that, you will get the distance of the centroid of this I section YT or Y bar. So Y bar itself is YT here. T stands for distance from the top fiber. So once you locate this, now calculate the moment of inertia of this I section using parallaxis theorem, which I have already explained. So using parallaxis theorem to calculate that, you will be getting the I value here. So this is the I value. This is the parallaxis theorem which is used. So try to work it out. Okay. So YT you are getting 111 millimeter. I value you are getting this. So this is very important. When they give I section and T section, I value you have to calculate. For standard sections you will be knowing. For rectangular section, I is BD by 12. Circular section, I is pi d power 4 by 64. Those things. And for triangular section, you have BH by 36. Those formula you know already. But for I section and T section, if they give whether symmetrical or unsymmetrical, you have to compute the value of distance of centroid, and then you have to compute the value of moment of inertia about that centroidal or neutral axis. So this is what you have to do. Then you calculate the shear stress at all the at how many points you need the values of shear stress. So at the top fiber it will be 0. Please note that shear stress at the top and top fiber and as well as at the extreme fiber. Top means the extreme fiber, farthest fiber. It is 0. So 0, 0 here. Okay. But it will change two values. It has got two values here at the junction as well as here. So when you are finding the shear stress at this junction, for bottom of flange you have to take B is equal to 100. Top of web you have to take 20. B is equal to 20. All the other things remain same. Okay. When you are calculating the shear stress here, for the bottom of the for the top of bottom flange. We can call it as top of bottom flange. B is 150. But for bottom of the web bar, B is 20. Once again, you have two values here. And A into Y bar, you should be very careful. So when you are calculating A into Y bar, for example, if you want the value of A into Y bar here at this junction, above this whatever area is there, that we have to take 100 into 20 into distance of centroid of that area from the neutral axis we have to take. Okay, so it will be how much that will be. So this total yt will be there. Yt minus 10. Yt minus 10 is the distance of the centroid of this flange from the neutral. That is y bar when you are calculating your shear stress for this level, at this level. Okay. So y bar value, A value remains same. Only B value will change. You can see here. So shear stress at the bottom of top flange formula is this. F is 60 kilonewton. So 60 to 10 cube divided by B is you have to take 100. So because width of flange is 100, B is 100. Then I value we have calculated using parallaxis theorem. This is I value into A is that area of that flange above that layer 100 into 20 into distance of CG. See here. So yt is 111 you have got minus 10. Minus 10 we have to take because here. So this distance from the neutral axis to centroid of this, that is y bar. Okay. So that is your A into y bar here. Same expression will be there. Only difference is B is equal to 20 we have to take when you are calculating shear stress at top of web. See, so shear stress at top of web will be, see here, after this, we have got this, then shear stress at the same level, but in the web. So you can take, but in the web, then B is 20. So only that B will change. Here for flange it is 100, for web it is 20. Remaining terms are all same. See here. So this is the value. So it changes from 2.61 to 13.0. So that is at that level. Similarly, if you are calculating the shear stress at this junction, if you are calculating the shear stress, what you have to do is, so for the flange, you take below this whatever area is there, not above. Now you are moving down, you know. So since you are moving down, so you have to take the area below the neutral axis. So here, if you are taking this level, what is the area below this level? 150 into 20. So 150 into 20 is the small a value. Y bar is the location of the centroid from here. Okay, location of the centroid of this area from here, which is nothing but how much? That will be you will be having how much? Area is 150 into 20. 150 into 20 multiplied by, so this distance will be 200 minus yt. 111 you have got, you know. So 200 minus 111 means it is 89. So this total distance is 89. 89 minus 10 we have to take, that is 79. So 150 into 20 into 79. That is the A into y bar here, or this, below this. See here, it has been done here. You can see here. So later on we calculated the neutral axis. See at the junction of web and lower flange. Junction of web and lower flange. So first we have to take the web, then we have to take the flange, because it is in the other way. When you are moving down from web to flange, first value of B will be 20, then second value of B will be 150. Okay. So this is your area 150 to 20. Distance I told you, 190 minus 111, which is nothing but your 89. I think it is 89. It is 190 minus 111. Not 180. This is 200. Should be 200. It is not 180. Total is 200. There is a mistake there. See here. This is the centroid. This is the centroid. From here to here, we are getting 89 minus 10, 79. Yeah, it is 79. Yeah, both are correct. So 190 minus 111 is the same as 79. You can take. So 79 is your y bar value. Now, once you get that A into y bar value, so you can calculate the values at these 2 points. So junction point you have one value of B as 20, another value of B as 150. Now let us see how the neutral axis, at the neutral axis level, how the shear stress is calculated, because at the neutral axis level also it is important, it is maximum there. So at the neutral axis level, if you want the shear stress value, so at the neutral axis level means here, your B value will be 20, but A into Y bar value will be different. So when you are taking A into Y bar value, take all the area above this neutral axis. So all the area means this flange area and this web area. So that corresponding area should be multiplied by the respective distance of CG. So for the flange portion, area is 100 into 20 into Y bar will be from the neutral axis to the centroid of this, which is how much? From the neutral axis to centroid of this means 111. This weight is 111. 111 minus 10. It becomes 101. So 101. So A is 100 into 20 into 101. That is for the flange. Plus A into Y bar for this red portion. Because I am calculating shear stress here, I have to take the area above this. Or you can take area below this also and you can calculate. So web portion area is now here 111 minus 20 is the depth. That is, it comes to be 91. 91 into 20. 91 into 20 is the area of this web into distance of CG of that web from the neutral axis will be how much? Distance of CG of this web, this portion. So this is actually totally 34.42 minus 20 means, 34.42 is this minus, 111. 111 is this much. 111 minus 20 means 91. 91 divided by 2. You will be getting 45.5. So area is 20 into this, 20 into 111 minus 20. That is 91. 20 into 91 is the area. Into 91 divided by 2 is the distance of center. Okay, that is A into Y bar for the web. So A into Y bar for the flange plus A into Y bar for the web, we have to add to get the shear stress in the neutral axis level. That's what he has written here. Shear stress at neutral axis, A into Y bar for top flange plus A into Y bar for web above the neutral axis. This is the value. Now you can, this A into Y bar, is area is in millimeter square, Y bar is in millimeters. So if you multiply, you will get in millimeter cube. Now this value of A into Y bar, you have to put in this form. The F is same, B is 20 at the neutral axis level, width of the web is 20, I value remains same. This is A into Y bar. If you simplify that, you will be getting 18.37. So this is the highest value of shear stress, which occurs at the neutral axis, 18.37. So if you plot the shear stress distribution, you have two values here, you have two values here, you have maximum value here. So this is horizontal line, this is horizontal line, whereas this is a parabola. So this is how you have to plot the shear stress distribution diagram, which is a parabola for T section and I sections. So three problems I have explained today. Same problems, you try to work it out in your notes and try to understand. Procedure is same, formula is same. Only thing is what is that Y bar, how to calculate A into Y bar. So those things you should practice. Then you will get the answer. For the same problem, they may ask you to plot bending stress diagram. Bending stress diagram is a straight line. So you have to draw a vertical line like this, compression and tension here, this side. That also they can ask. So in the exam, they can give T section or I section and they may ask you to plot bending stress diagram as well as shear stress diagram. For 10 marks, they can ask that. They will give the value of bending moment and shear force. So if you know the bending moment value, using bending equation, M by I is equal to F by Y, you can calculate the bending stress at the farthest fibers, and at the neutral axis it is 0, and the point should be joined by a straight line. That is bending stress distribution. If you know the shear force value, so F divided by B into I into A into Y bar. So that is your shear stress. So if you know the value of F, shear force in kilonewton, that can be substituted in Newton, and you can get the values in Newton per mm square. So all these stress values, whether it is bending stress F or shear stress Q, they are in Newton per mm square or MPa. So that's why you should be very careful about units. When bending moment is in kilonewton meter, you have to convert that into Newton millimeter by multiplying by 10 power 6. When shear force is given in kilonewton, you have to convert that into Newton by multiplying by 10 cube. So those conversions, you should be very careful because stresses are always expressed in Newton per mm square. Okay. So I have explained in detail the shear stress distribution for all the types of sections. Bending stress distribution also we have done problems. So you have to practice. So I am going to give in the third assignment, I am going to include all these problems on bending stress and shear stress. For the test, whatever I have done till now, till this class, that will be there. So as usual, 5 questions will be there. So you will be 2 internal choice questions will be there. 3 questions will be compulsory. So starting from thick cylinder and thin cylinder in module 2, so you need not study that this thing. What is that? Plane stress and plane strain that I have been given, problem I have given in the first test. I am not going to give problem on that. But in module 2, thick cylinder and thin cylinder derivation and problem I have done. Then module 3, bending moment diagram and shear force diagram complete. This module 3 complete. So there also I have done so many derivations and problems, plotting of BMD, SFD, point of contraflexion, point of zero shear. So all those things, how to draw the bending moment diagram, how the profile will be, given the shear force diagram, how to find the bending moment diagram, all those things I have explained. Then special cases for different loading cases, simply supported beam, cantilever beam, how the BMD and SFT will be when concentrated load acts, when UDL acts, when UVL acts, when external couple acts, all those things I have explained. Then coming to the fourth module, we discussed about the bending stress and shear stress distribution in a beam, and we have derived the pure bending equation or simple bending equation, section modulus, modulus of that is what you can modulus of rupture or moment of resistance or moment carrying capacity of a section, definition for all those different types of sections. Okay, so these things we have done. All the things you have to note down. In the afternoon class, I will just revise some topics, which is for the test. You can just attend that BMD, SFD, and this bending stress and shear stress. Some 2 or 3 problems I will just explain in the afternoon class. Don't miss that class. So I will stop here. So you have to work. So from my part, I have covered all the things. So you have to work. Then only you can understand the subject well. 18028.
Present, sir.
030.
Yes, sir.
19003.
Yes, sir.
6.
Present, sir.
5.
So 005.
5. Okay. 5, 6 over. Then 7.
Present, sir.
9. 10.
Present, sir.
11.
Present, sir.
12.
Present, sir.
13.
Present, sir.
16.
Present, sir.
16. 17.
Present, sir.
Present, sir.
18.
Present, sir.
19.
Present, sir.
Okay. Then next class at 3:15. I'll just revise some of the topics.
Sir, CV006, sir.
006. Yes, I agree.
Yes, sir.